Questo bottoncino rosso non mi ispira a niente.
No, questo non funziona più. Hi, everybody. Hope there is someone online today. Welcome to this section about service-oriented architecture within the software architecture course. So my name is Mauro Capuruscio, and I am associate professor here at the Department of Computer Science. So today we're going to talk about service-oriented architecture. So let's start by introducing what is a service. Okay, in general, a service is an act of performance that are offered by one party to another. And although the process might be tied to a physical product, the performance is essentially intangible. Okay, the essence of the service then is that a service is provided as an independent of the application using the service, and providers can develop specialized services and offer these services to many different users at the same time. Well, we have the same if we talk about a software service. Then we exploit this definition, and a service is then defined as a loosely coupled, reusable software component that encapsulates discrete functionality. Okay, and this functionality might be distributed and programmably accessed. And in particular, what we will talk about today is about the web service, okay, which means a service that can be accessed through the internet, and by means of all the standards that we are use on internet. Then, in this case, the essence of the service is to be a reusable components, okay, that are independent and loosely coupled. And then we're going to understand what this means. But the main important concern is that a service can be seen as a component. And then what is a component? Well, it's just a component in a nutshell is a software element that conforms to a component model. So we have some rules, we have to conform to these rules, and when the rules specify how to program the component, how the components interact each other, how to access the component, and how to specify the set of services provided by the component. This component can be independently deployed, which is very important. It means that you don't need to satisfy all the dependencies in order to deploy a component. And these components can be composed one each other in order to implement complex systems. Very important, components are always specified by their interfaces. So, I mean, you don't care about how you program, about the programming language or the specific technologies. What's matter is the set of methods or services, functionality, that the components provide. Okay? And this allows to have a real and clear separation between the interface, the set of functionalities provided by the component, and the implementation. Then every single component, well, these components should comply and conform to standards. Okay? These standards allow us to facilitate the component integration. They define how the interface is specified, and then this means that once you specify the interface, you are also able to read and understand these interfaces, and how the components communicate each other, which means type of messages and the underneath protocol used to let component interface each other. Another important aspect of this component-based software engineering is the presence and the support provided by a middleware. A middleware is the infrastructure and is a software layer that provides and is in charge of managing the component lifecycle. He takes care of allocating memory, managing the communication between the components, allowing and checking access control to the components, and so on and so forth. So there are many different middleware, and each middleware offers different type of services that can be exploited. Usually, a component has this shape. So the components specify a set of required interfaces, which are the set of functionalities that are needed to in order to run the component. Okay, so you can deploy the component into isolation, but in order to work properly, so you might need external functionalities provided by other components. Okay, this is as we will see later, this is the aim of the component composition. On the other way around, a provided interface defines the set of services or functionalities that are offered by these components to other components that participate into the composition. One important architectural property for the components is that they are loosely coupled. Okay, coupling usually occurs when there are many interdependencies within the components. And usually, if we have a network of interdependencies, this is very bad because it makes very hard to understand how the components work and how they interact each other. And suddenly it can happen that if you make change in one component, then this change can affect all the other components that are connected to the one that we are modifying. Then, what we need usually is to strive for loose coupling. Okay, a loose coupling system is a system where each component has little or no knowledge about the other component. So the less is the number of interactions and dependencies that we have in the system, the better the system is. Okay, because it's much more easy to maintain the system, understand the system, and if we make any change in one component, then we don't have too many effects on the rest of the remaining components. Then, one introduced this component-based software engineering, which is as the foundation for a service-oriented architecture. So let's see how we can build on top of these few concepts in order to build a service-oriented architecture. So services, differently than components, are standalone and loosely coupled. Okay, so that's very important. So a service, usually you use a service and the service it works. Services, they can operate in respect of their execution environment. Okay, you are not tied to any specific platform. You can use services that are deployed remotely. Services rely only on the message-based communication, so you don't have tight communication and stateful communication between the services, at least in theory. Then we will see that in practice this is not really true. And the services are implementation language independent. So you can have services developed in Java that can interact with services developed in C#, for example. What's the benefit of this type of paradigm? So services can be offered by any service provider inside or outside an organization. So this means that you can create services that can be reused within your organization. For example, as manage the payment of bills or a service that take care of managing employees, for example. And this service can be used either by other services within the same organization, but also from different organizations. For example, you might choose to use PayPal for paying bills. It's provided by an external third-party entity. Organization then can create this very complex application by integrating these standalone services that can be provided by themselves or by external partners. Service providers usually make information about the service public. That's very important, so that other authorized user or authorized organization can find the service and make use of the service. That's then we will see how this is possible. And then another important thing is that you have a lazy coupling between the services. So you can delay the binding of services when until they are deployed and you need them. Okay, that's pretty different than when, for example, you have an object-oriented programming program, then you have to compile in order to bind one class to the other. Or with respect to a component-based system, that the binding is made at deployment time. In the case of services, the binding is made at runtime. So when you need the service, you just open the socket, contact, make a connection within the service that you need and execute the service. Then this allows for an opportunistic construction of the services. Okay, so service providers may create new services by just linking many different existing services. Okay, and then how to do that by means of service composition that we will discuss in a while. Then, on the other way around, service customers can pay for services according to their use, for example. I mean, you don't buy the service, but you can buy the access to the service. Okay? For example, you can pay for every use, or you can pay for flat. I mean, I can pay for just using a service for one month, for example, or for every single interaction. In this way, applications are smaller because all the business logic resides on the side. Okay, and that's very convenient, for example, when you implement mobile application. Okay, for example, in mobile devices that have a limited processing memory capabilities, then you can offload all the computationally intensive processing to the web, the server side. So let's see first example, just to understand why services are important and how we can benefit from this new architecture and paradigm. So let's suppose we have an in-car information system that provides drivers in a car with different type of information about the weather, the road traffic condition, or the some local information, for example, about restaurants or hotel, or so on and so forth. Okay. This information system is then linked to the car audio system, and then well, whatever you retrieve information, this information can be that information are delivered as a signal on a specific channel. So the car system can speak what is the type of information that is downloading. The car system, it's very important, is also equipped with a GPS receiver that allows you to know what's the position of the car. And based on that position, the system can access a range of different information services. Okay? And then also important, another functionality is that this information may be delivered to the driver in different languages. For example, in my case, this will be in Italian. Then let's see how can we implement this type of scenario. So this is the diagram of the different modules that we have embedded in the car software system. So we have the radio, we have the locator, which is the GPS antenna, and then we have also a receiver that receives information stream from the services and forward this information to the radio, okay, that speak and translate digital into stream to radio signal. Then we have a transmitter which is in charge of sending the position, the current position and the information request to the set of services that are available in the surrounding. And then of course we have the user interface that allow the user to interact with the system. Then on the remote side, so outside the car, what we have is a set of services. Okay. Very important is this service discovery. Okay, this is an engine that allows us to find available services. Okay, in our case, we use this GPS position in order to find the services of interest. And then we have this remote collate mobile info service, which is the service that try to find out different type of informations that are concerning the GPS position of the car, collecting them, putting them together, and then sending to the translator that finally send back this information in the form of the stream. And then as we can see that all these systems are systems that are provided by third-party providers. Okay, these are services that exist independently of the in-car information system. Okay, so the weather info, it exists even if for peoples that are not using this our own in-car information system. Okay, this set of services exist, they are available on internet, and then so the idea of a service-oriented architecture that we can exploit the set of services that are really available on the internet. Note that we have a special entity, which is the service discovery entity. This is part of this service-oriented architecture paradigm, and then we're going to describe it better soon. So the idea is that all the available services, all the services available on internet are registered in this service discovery, and then you can find them. I mean, as you do by using Google when you have a specific web page, and then you want to search for this web page on the search engine. Why exploiting SOA for making this application? So what's the of advantages. So if we use a SOA approach, where it's not necessary to decide the design and deployment time, what type of services and what type of service provide we should use. Okay, so for example, we can time what type of weather forecast service use. Okay, and then what we we are not is not necessary to decide what specific service to be accessed. So we use weather forecast from Google or from Microsoft and so on and so forth. Okay, so we can decide the runtime when we need them, not during design or deployment time. And then, as the car moves around, so the in-car software uses the service discovery to find the most appropriate information service to bind and to consume. Okay, for example, if I am traveling through Germany, I might use the weather forecast from, well, instantiated in Germany, because it might be much more accurate than the weather forecast provided by a US company, for example. Or if I travel through Rome, for example, I can search for restaurants that are in that area. Okay, I don't care, of course, of restaurants that are located in Veco if I'm traveling far away. Okay, then that's something that we can do only because we have this service discovery in our system. And then, because of the use of this translation service, so the car can move across the borders and then and make local information, for example, the weather forecast in German, made available to people who doesn't speak German, for example, like me. So let's see then, and deep inside to the software-oriented architecture. So what is a software-oriented architecture? So the idea of having this service-oriented architecture is we want to develop a distributed system where the building blocks are standalone services. Okay, services are independent and standalone. They exist, they are running somewhere in the network, and then we want to exploit them in order to create more complex application by means of service composition. Services may execute on different computers from different service providers. Okay, they are spread out the network. Very important, they must use a standards protocol. Okay, because so we need standards in order to let these services interact each other in a way. Protocols in order to make services interacting each other and exchange information. So usually the service-oriented architecture paradigm defines three architectural entities. We have a service provider, okay, which is the one that implements and offer the service. The service is usually described by means of WSDL. WSDL is an XML-based language that allows to describe the set of functionalities provided by the service. So once we have this description, we can publish it into the service registry, which is the service discovery system that we discussed before. Once this description is public available in the service registry, then a service requester can make a query to this registry in order to find the service he's interested in. For example, let's suppose I need for a weather forecast service, then I can contact the service registry, search for service provided with this specific service. Then the service registry will return a list of all possible, all available services that match my query, and then the service requester, which means the service consumer can well select among all the services available in this list the one that best fit his needs. For example, the one that is closer to my location. And then I can bind. So once I found this service, then I can bind to this specific service and consume it. How do that? We do it by exploiting this SOAP standard protocol, which is still based on XML, and then it's understandable and is used for machine-to-machine interaction. So what are the benefits of exploiting this type of paradigm? Services can be provided locally or outsourced to external providers. Doesn't matter, because now we exploit stuff. Doesn't matter that the service is running on a local machine or remotely from third parties providers. They are language independent, so it means that a service implemented in Java can interact with the service implemented in C#, for example, or in any programming language. Investment on legacy system preserved, because I mean you can wrap up a legacy system behind. I mean, you can expose the functionalities provided by a legacy system as a service, okay, by wrapping these functionalities and publishing them into the service registry. And these also allow for inter-organizational computing, because it facilitates the interaction and information exchange between different organizations. That's why, for example, you can integrate PayPal services with Google services, for example, and make your own system. As we say many times in this early few minutes, I mean, one key aspect of this paradigm is the composition. So how we can compose one service with another in order to create more complex services. Okay, and then so let's see what is this service composition and what type of service composition we can do. So the idea is that existing services can be composed in order to create composite services, okay, and application. And of course, these composite services and application are much more complex of the single services. The base for a service composition is usually a workflow, okay, which is logical sequences of activities. For example, here we have a workflow for providing a travel reservation, okay, that allows you to book a flight, book the hotel, and then arrange a car taxi, and then once you arrive to the hotel location, we can browse for attractions and book this attraction. Okay, this is a set of activities defined as a flow show, a workflow. So the idea is that every single activity can be implemented by a different service. Okay, for example, we can use I don't know, SaaS web service for booking the flight, and then we can use booking.com for booking an hotel, and Uber for arranging a taxi, and then we can use, I don't know, TripAdvisor for browsing the attractions and book the attractions. Okay, so 3 different services, 4 different services provided by 4 different organizations. Okay, and then the idea is that we can create and run this workflow by aggregating and composing these services that are provided well, as a standalone. I mean, this booking.com service, okay, it exists independently of Uber or independently of TripAdvisor. Okay, they are completely standalone, but we as a consumer we can compose them in order to create well, a more complex service, which is this travel reservation service. So how can we integrate or compose this service? So there are two main modality. Okay, we call orchestration and choreography. So what's the difference between the two? As you can see, the orchestrator is usually used in the private business process. It concerns having a central process, which can be another service, of course, and this central process takes the control of all the involved web services and coordinates all the interactions and execution of the different operations. Okay, for example, we have this central orchestrator, which can be our own service that first interact with the SaaS service in order to book the flight. Then once we got some result from this web service, we'll invoke the second service, the one from booking.com, for example, for booking an hotel. And then so once we have the location of the hotel, we can invoke the web service 3 in order to search for attractions around the hotel, and then finally we can invoke the service number 4 in order to book for these attractions. The very important thing is that all the involved services don't know nothing about each other. Okay, they really don't know they are part and involved in a composition. I mean, as said before, booking.com, I mean, he knows that, I mean, he's a standalone. I mean, doesn't matter for them if they have been used by a human or by another machine. Okay, that's very important. So who knows what's happening here is the central coordinator. Okay, the central coordinator, which is the orchestrator, it's the only one that is aware of the global goal, I mean, which is to make the reservation, okay, of all different activities. Usually the orchestration is centralized, okay, and has the explicit definition of all the operations that he needs to execute and the specific order. Okay. This is another example of for the hotel booking workflow. For example, it's still one of the services working internally. Okay, for example, we have the customer, and then what we need is only to understand which are the interactions between the customer and the remote services. On the other way around, choreography is quite different. Okay, in contrast with respect to the orchestration, choreography does not rely on any central coordinator. Okay, rather here in this case, every single web service involved in this choreography must know exactly when to execute its own operation and with whom he needs to interact. Okay, we say that choreography is much more collaborative with respect to choreography because the idea, I mean, it focuses on the exchange of messages, okay, in the public business processes. So each service must be aware of the others and all the services must be aware about the goal that they want to achieve together. Then this means that they must know the business project, the process, all this, the operations that they need to execute, the specific sequence of messages and operation that they must execute, and the timing of messages exchange. Okay. As you can see here, we have two different workflows, and they interact. Okay, so we have we start, for example, as a request processor. Then we send a message in order to check the availability, and then the availability send back a message, and then we can use this message in order to run all the other activities. And then, as you can see, different activities in one service interact with others activities in the other service, and then they must know how to interact each other and when interact each other. Okay, then it's not a black box. Here we need to specify everything. In the previous case, instead, we only know which is the behavior of this one service, but not what is the behavior of the customer in this case. Okay, that's a very important distinction between choreography and orchestration. So, which one to use? I mean, as always, there are some pros and cons for each paradigm. Some pro for the orchestration, it's centralized, and then he runs only in one machine, takes control on everything, and then this means that it's much more easy to understand with respect to the choreography, which is instead very complex. It's simple to design, administrate, and allow us to select, to run dynamic selection, so we can change the remote service at runtime. For example, we can substitute at runtime booking.com with a different booking service. And then it's very easy to recover from errors, because I mean, everything, all the logic is centralized. Then you know if something goes wrong, you can recover from it. But it's also, since it's centralized, then we have a single point of failure. Okay, then the centralized server can be a bottleneck, and this can prevent high performances, and then also scalability, because I mean we have a single point of access, and then if we have many different clients that access the orchestrator all together, so we can degrade the quality provided. What about choreography instead? So there are some pro. It's very nice. We want to achieve for scalability, because we distribute the load of the operations. Increase the availability, because we don't have any more single point of failure, and also the efficiency, security, and flexibility of the system. But at the same time, it's much more difficult to design and understand, and we need, since all the different parties must know each other and agree on the protocols and interfaces, it means that it's much more difficult to design, implement, control, and administrate. I mean, if we have many different parties, I mean, we need to find out an agreement between them. Okay, that's much more complex. But I mean, as you can see, we have a lot of pro. That's why it's very nice. So now we discussed some concepts behind the service architecture. So let's see how we can implement SOA in practice. Okay, there are mainly three different types of service technology that we're going to discuss. We're going to discuss about web service technology, RESTful service technology, and then the micro service technologies, which is very new. So the first type of web services was underpinning XML technology. Okay. So we have the transport layer that is implemented by means of internet standards, in particular HTTP, HTTPS, and SMTP, UDP, and so on and so forth, all the standards that are available in internet. On top of this layer, there's been introduced a new layer, okay, that exploit XML technology. So we have, as we introduced before, we have the SOAP protocol that is in charge of communication, then defined how two different services can exchange messages. Then we have the service definition, and in particular we have WSDL, which is a language that allows us to describe the functionalities provided by a service. And then we have UDDI, which is a language that allows us to implement service discovery. Then we have some process language. In particular, we have a web service Bible, which is a language that allows us to express composition. Okay, then both orchestration and choreography of a service. And then we also have a high-level set of services that are implemented on top of this stack. Okay, some support services, for example, for security, addressing, transactions, and so on and so forth. Okay. But the three key standards for implementing a web services are the SOAP, okay, as said, which is a message exchange standard that supports service communication and interaction. Then we have this WSDL, which is the standard that allows for specifying the service interface, then the set of functionalities provided by the service, and its bindings. So it means how to access the specific functionality, which is the set of parameters, and what's the return type of this function. And then the WSDL, the WS Beeple, which is the standard for defining the service composition. So this is much more information about how this business process execution language, which is the Beeple, works. Okay, there's been having the idea is that having web services exposing their functionality is not enough, because all the value of service-oriented architecture rely on the composability of the services. Okay, if the services cannot be organized in the composition, they are not so powerful. I mean, we don't need services. We can just use any other paradigm, architectural paradigm. So the idea is that Beeple allows and facilitate the composition of web services. Okay, and then it can be used for long-running processes, something that you now and then you run, that you use for running your own business. Then this is very powerful, and then but suddenly, well, not suddenly, but after a while, people start discovering that these XML-based standards, okay, this XML-based stack, technology stack was too much heavy. It was very heavy because you need to parse XML and XML is very inefficient. So the idea is that to exploit a different type of architectural style, and in particular the REST, which is an architectural style which is based on transferring representation of the resources from a server to a client. Okay, well, this is the architectural style that underneath the internet as we know it. That's something that we use every day. And you might be also familiar with this type of architectural style. It's much simpler than exploiting SOAP and WSDL for implementing web services, because I mean we just use low-level products and that are much more flexible and easy to use. Then they are much more lower overhead with respect to these big web services that we discussed so far. In order to implement REST web services, so we have three main concepts, okay, that are really key. First, REST, and in particular these uniform interfaces. Okay, REST, as we will see, is an architectural pattern, that revolve around this very important feature. Okay, so the fact of having a uniform interfaces. So all the services provided in a RESTful application must implement the same set of functionalities. Then we rely on HTTP, okay, which is a broadly available transport protocol in internet. And finally, we rely on JSON, which is very simple data representation format. That it's much more efficient than XML. Okay, I mean you can parse a JSON packet much more easily than an XML packet. So, but let's go to the software architecture. So the architectural pattern behind REST. So the REST architectural pattern essentially defines two main architectural entities, which are the user agent, which is the one that who initiates the interaction, and the origin server, which is the entities that provides the service. Then also the REST architectural pattern also defines other two additional architectural entities, which are the proxy gate, the proxy, and the gateway entities. These, I mean, are used only for achieving scalability. Okay, but they so we don't need to know now what they are doing. Okay, they are used only to increase the scalability of the system. This type of architectural pattern relies on four design principles, which are very important. First, addressability. Oh, well, sorry, I forgot to say. A very important entity in this representational state transfer is the resource. Okay, every single origin server maintains a resource. A resource is the state. Okay, so every single origin server has a state. This state is known as a resource. Whenever a user agent will send a request to a origin server, then the origin server sends back a representation of this resource. Okay, and then the representation can be, well, we can have many different representations for a single resource. For example, a resource can be I don't know, a record in the database. And then how you can represent a record in a database. Well, you can do it in many different ways. You can send back a PDF, which representing the data memorized and stored into the record. You can send back a web page. You can send back a picture. You can send back a Word document. Okay, all of them must represent the same resource. So once we have this, it's very important to understand the different principles that define a REST architecture. First, addressability. Every single resource must be identified uniquely by means of a URI. Okay, I mean, whenever I need something and something is published, then he's identified with a specific URI. Then stateless, all the interactions between the user agent and the origin server are stateless. Stateless, it means, I mean, we are talking about the interactions, not the entities. So the entities can have their own internal state, but the interaction between the two entities is stateless. Okay, we don't keep any session, let's say, between the user agent and the origin server. This means that whenever you ask for a service, the user agent has to provide all the information required for running the functionality, for accomplishing the functionality. Then connectedness. This means that all the resources can link to each other in their representation. Okay, that's what we have when we navigate the internet means of links. You connect a web server returns a representation of its internal data, a web page, and then within this web page you can find links to other resources, okay, that are other pages or other servers around the internet. And then very important is the uniformity. I mean, all the resources implement the same case. Okay, all the resources available in this architectural pattern implement the same set of functionalities. So, which are the architectural constraints behind a REST architecture? First, it's client-server. Okay, there is a separation, clear separation between the client and which is the user interface, and the logic behind implement the real application. As said, stateless, there's no client context on the server, so the server will never, well, should never take the status of the interaction between here and the client side. Okay. So I know we, when we implement application on internet, we always use session. Well, session is something that we build on top the REST pattern. Okay, the pattern itself does not implement any session. The sessions are something that we implement at the application level, not the architectural level. Cacheable. So this allows to reduce the interaction between the client and the server. So all the information that are exchanged in this part. We have code on demand. It's very important. We can execute. I mean, we can download, for example, code that can be executed on the side. That's something that it's quite very common whenever you have JavaScript. You access a website and then you download code written in JavaScript that run on your own browser. Okay, this code is not run on the remote site. And then the uniform interface. Okay, we know we use the well-known HTTP verbs for manipulating resources. Okay, this means get, put, post, and delete. And then we have this hypermedia as the engine of the application state. Okay, that's very important. So, in order to implement a RESTful application, we need to exploit this. So, the idea behind this constraint is that the response that you get when accessing a remote operation should allow, contain all the set of allowed. That's something that we have whenever you put some items in your cart, for example, while buying stuff on Amazon. Okay, you see something, you put the item of interest in the cart, and then when you access the cart, you have you have links to the state. I mean, check out the cart, for example. And these are the three main aspects that make REST very powerful in order to build up a web service. Okay, stateless, uniform interface, and hypermedia has the engine of the application state. These are the three main key concepts that we need to exploit in order to make very powerful RESTful web services. And then we about the resource. Resource fundamental element in a RESTful architecture. That's very important. So, as anticipated, mentioned before, a resource is simply a piece of data. Okay, it's a data element that can be a catalog, a medical record, a document, or this slide set. Doesn't matter. It's something. It's a piece of data that you are interested in. And with resource, every single resource can have, mentioned before, can have many different representation. That means many different formats. For example, a catalog can be represented by means of a Word document, or a PDF Word document, or a web page with links, okay, and so on and so forth. In resource, usually we can make 4 different types of operations. We can create a resource, we can read resource data, we can update this piece of data, or we can delete. And then before there is a straight mapping between these general operations and the set of verbs defined by the HTTP protocol. Okay. Then, in order to create a resource, we use post. Okay, in HTTP word. In order to read the resource, we can use get method implemented by HTTP, and then we have put for the update and delete for delete. Okay, and then by means of these 4 methods, then we can create very complex systems. It's very important. So there are many different, many other operations defined by HTTP. But I mean, the 4 important, the most important in our case is get, post, put, delete. Some of them are safe, okay, but have to take special attention to the post method, which is non-idempotent. Okay, what does it mean? Idempotent method means that if you call this method many different times, you always get the same result. For example, if you get 10 times, different times the same web page, you always get the same the same result. But this is not true when you post something. Okay, the post is very tricky because there is not a clear stick behind the post. You never know what the post is if you don't have a clear specification from the API, and it's not safe because, I mean, if you make two posts, different posts in a row, then you can get different results. Okay? Important to know. Then HTTP already provides many mechanisms for caching, for content association, so you can negotiate the type of representation for the specific resource that you are interested in. Okay? You can access a specific piece of data and then negotiate if you want this piece of data has a web page or a PDF or other different type of data. And there is a clear identification between user agent and server. For example, whenever you issue a GET to a website, that website can understand if you are issuing this GET from a desktop or from a mobile, because can recognize if a user agent is a browser running Android or is Chrome user running on a desktop device. Okay, then there is a clear identification of the type of user agent and server. Then you can easily recognize what type of user agent server you're using. And then, very important, status codes. I mean, the status codes must always be included into the response, because allow the client to understand what's happening. Okay, if we get 200 code, means that everything is going well. If we get 404, it means that the resource that we are trying to access does not exist. Okay, then HTTP defines many different status codes, and then it's very important that we exploit this status code in order to understand what's the behavior of our application. Okay. And then HTTP provides a really good and standardized interface. Okay, it's everybody is knows what is HTTP and they use XHTTP. Of course, we don't have any silver bullet in this life. Then we might have some disadvantages as well for this RESTful approach. And in particular, the most important disadvantage is that whenever we have a complex interface for a resource, we cannot easily define it, because we only have 4 different methods that we can build upon. Okay, still get, put, post, and delete, and it's very difficult to create complex interfaces, complex operation building on these 4. Then there are no standards for describe the interface for a service written in a RESTful way. Okay. We discussed, we have WSDL for describing the set of functionalities provided by a web service, XML-based web service, but we don't have any interface description language for RESTful web services. And then when you have really to implement your own infrastructure for monitoring, managing quality of service and service reliability. Okay, it's much more easy if you exploit SOA web services, XML web services standard, because the infrastructure also provides this stuff of super services. Okay, then one easily turnaround for this problem is to whenever you have a resource, you can provide 2 different interfaces. Okay, you can still provide a SOAP-based API and a RESTful API. Okay, so that someone can use the SOAP-based API and someone else can use the API. So now, before starting talk about the microservice technology and microservice architecture and technology, so let's have 5 minutes break. So, be right back. So let's start over. Then next evolution of service-oriented architecture is toward microservice. So microservice, as we will see, not introduce nothing more groundbreaking idea to the service-oriented architecture paradigm, but just make some to put, well, some concepts already introduced when at the beginning of the lecture to the text. So the idea that microservice architecture defined by functional system decomposition on into very small micro services that are manageable and independently deployable service. I mean, so the key concept here is the size. Okay, so first, functional system decomposition be vertical. So, well, in contrast to other types of software architecture, here the decomposition should be vertical. As we will see, every single service must implement all the specific everything he needs. Okay, we go on this concept in the slides. Then they must be manageable. This means that microsystem should be very small, and every single microservice should be managed by a single development team. Okay, by following this two pizza rule. Okay, so if a team can well, feed with 2 pizzas, then it's a good amount of people, of members within the team. Okay, then I mean, with 2 pizzas, you can feed almost, well, let's say 4 people, depending on the size of the pizza, of course. But let's say, by the way, 2 pizzas can feed only a small team, and then a small team should be enough in order to manage and implement and manage a single microservice. And then another very important aspect is the independent deployability. Okay, there should be a share nothing architecture. I mean, every single microservice should be deployed independently on the others. Okay, they shouldn't share machines or virtual machines or memory or storage, nothing. Okay, every single service should be fully functionally complete. Then it means what relies on the functional system vertical slicing. Okay, then must be small and then manageable by a small team, and then should be completely independent. Okay, vertical slicing. So this means that every microservice is complete. Okay, he will provide for resource representation, which means the interaction and the data management. Every single service has its own database. For example, you don't have a shared database. A database which is shared by many different services. In this type of architecture, every single microservice has its own data management system. And every single microservice should handle one resource. Okay, then we should have a microservice for client, one microservice for the shop items, one for the carts, one for the checkout. Okay, well, if you take a monolithic or web service approach to this web shop. Okay, you don't have, usually you have only one big database where you store all the data concerning the clients, the items, the cards, the checkout, the bill, and so on and so forth. Instead, with microservice architecture, I mean, we are forced to slice the application logic vertically, and then it means that every single microservice should be complete, from data representation, from data management up to the resource representation and the user interface. Okay, but very important, they must be small. Okay, still font-sized services, small and manageable by a small development team. How to make this verticalizing? So usually, well, so far we start, I mean, we have a large problem to solve, and then it's very easy usually to provide the monolithic solution logic that will implement and solve the large problem. For example, we want to sell items on internet, then we create a big web application for selling these items, and then usually all the data is stored in a big database, and then we can apply this three-tier software architecture where we have an horizontal slicing. Okay, we have data management on the bottom, and then we have the application logic in the middle, and then the user interface and presentation, let's say, on the top level. Okay, but now what we want is to split and divide the application by applying the separation of concerns theory, so that we can split the big problem into a set of smaller problems that cause concerns that are much more easy to solve, and then create a collection of units of solution logic, one for each small problem. So the idea is that we have a large problem, we divide the large problem into a set of smaller problems, and then for each small problem we create a specific microservice, okay, or well, a specific functionality. So once we have this decomposition from a big problem into a set of small problems, and then we create a small solution logic for each sub-problem, then we can deploy every single solution logic unit into a microservice, okay? And then every single microservice will encapsulate the logic for solving a specific sub-problem with respect to the big problem A that we've seen before. Sorry, I lost you guys. Okay. And then these small solution logics units are then encapsulated and exposed as microservice. Okay, there must be no shared state and inter-process communication between all these solution logic. They must be independent each other. Okay, as said before, and fully functional. Here, the independent deployability is key for the microservice architecture. And what does it mean, independent deployability? Well, usually it means that we have different and separated code base for each microservice. Okay, So if you have 10 different microservices, you must have 10 different code base so that you can compile in isolation and deploy in isolation every single code base. You can use a different technology stack. Okay, for example, you can create one microservice using a Linux stack, another microservice running on Amazon cloud, and then exploiting the Amazon technology stack. If you have a separated independent microservice, you can scale them separately. Okay, you can turn on, turn down single web serve, single microservice instead of turn on and turn down the entire system. And then you can evolve independently features. So you can evolve one single microservice without affecting the other microservices. That's very important. And all of this is possible because we have this independent deployability. There are some architectural properties that are very important for when implementing a microservice architecture that we have to take into account. First, isolation and single responsibility. Okay, so a microservice should take only one responsibility. I mean, it means that should provide only one specific functionality. Okay, so components or services in this case must have only one responsibility. These components must be isolated, and isolated means they must have isolated persistence. Every single microservice should have his own database. They have their own domain model, user interface, implementation strategy, and development teams. Okay, everything should be independent from each other. Every single service should be independent of the others in this way. And it's very important this single responsibility. Okay, so if you take into account only one responsibility, then it's much more easy to keep the level and quality level of the architecture. But another important thing. So whenever, I mean, we say that composition is a key concept in service-oriented architecture. But composition put the system at high risk. Okay, then in order to mitigate the risk introduced by composition, we need to provide for robustness by means it means to improve in order to improve the interoperability and facilitate the evolution of the system. We have to make redundancy. Okay, so multiple components performing the same function, so that if one service fails, we have another service that can take over it and keep functioning, keep providing the functionality that we have. But I mean, redundancy is not enough if we don't have also diversity. Okay, so different services performing a same application must differ each other in terms of implementation, because if one of them have a specific bug, then and this specific we use the same. If we have bug in the microservice and then we use many different replica for redundancy of the same service, then the same bug will affect all the instances. But if we diversify the implementation for this microservice, it's very difficult, if not impossible, that different different teams make the same error when implementing a given functionality. Okay, that's very important. Then design principles with isolation and single responsibility must be taken into account when implementing microservice or architecture. Well, for example, a well-known application implementing or exploiting microservice architecture is Netflix. Okay, and then you can imagine how many users use Netflix at the same time, and then you need to scale every single microservice because of massive number of users that use the Netflix at the same time. And then if given microservice in this big architecture fail, and if you don't have redundancy and if you don't have diversity, this means that you fail in providing the the streaming, and then failing providing the streaming means a lot of money lost from the Netflix. Then in order to keep the system up and running, they have a lot of redundancy. Every single microservice is replicated many times, and then they also implement diversity, because if you have a bug on microservice, then you have the same bug in all the instances. And then in order to prevent this, avoid this problem, diversity is very important. So there are many microservice patterns that helps us to compose microservices in order to implement a real application. So since we are running out of time, I would just skip these few slides talking about microservice pattern language. Okay, they published this book all in this web page, microservice.io. It's a very nice page. You can find a lot of details about patterns. So just want to highlight some of these patterns. You can see we have a microservice architecture opposed to the monolithic. So the idea is that we want to break the monolithic architecture into a set of microservice architecture, and this is the core pattern. And then starting from this, we can apply different patterns in order to implement our own application. I just want to skip these few slides that you can see your own. They are quite clear, and then you can check the website, because I want to introduce you where is it? An example, and then talk you about the example. So you might be familiar with this Java Pet Store. Okay, so Java Pet Store is a well-known web application used for teaching and tutoring about Java 2 Enterprise Edition. Okay, essentially is a web application that allows you to sell items for pets. Okay, dogs, cats, and so on and so forth. Usually, Java Enterprise Edition based application has this software architecture. So we have a client interact with the browser, which is the client tier. The client tier interact with the web tier, which is implemented that implements the web front-end components. And then we have all the application logic tier, which is implemented in Java 2 Enterprise Edition by means of Enterprise Java Beans. And then this big enterprise business logic interact with the information tier. Okay, that implements all the key data regarding the catalog, the user database, the account database, and so on and so forth. Then, whatever the user need to do, he interacts with the web tier and then go through the application logic tier and finally access this information tier. This is a classical layered software architecture, and in particular 3-layered software architecture for this type of problems. Then what if we want to break this monolith and implement the same set of functionalities in a microservice-oriented architecture? Well, what we have is one. Okay, here we apply one of the patterns that are defined a few slides before, in particular the gateway. So we have our client that interacts through the browser to this customer web user interface aggregator. The user interface aggregator just interact with different type of microservices, and these microservices are implemented by means of REST API. So they are RESTful web services, but encapsulated within microservices. Okay, then we have the two different type of services that we discussed today in the same picture. Every single web microservice, as you can see, has its own database. This means that they are functionally complete. Okay, for example, the account service will provide you all the functionalities for managing the account. Then the shopping cart service provides you all the functionalities needed to manage the shopping cart, and so on and so forth. Same things for the order service and for the catalog service. Okay, and as you can see, the order service can, well, interact with external services. For example, we have a payment service can be PayPal, or the shipping service can be PostNord, for example, or the application service can be a text message to your own mobile phone. Then it can be a notification service implemented by Telia, for example, that they are external. Then here we have the same set of functionalities provided by the Java Pet Store in SOA style, well, in the usual monolithic SOA style, and then here we have the same set of functionalities but implemented by means of microservices. And then so if in difference, I mean, here in this type of application, if you need for scalability, so what should you do? Then to replicate the entire web application logic and then run this big monster in a new machine. Okay, and then you need to, well, include the load balancer that with respect to the incoming traffic will decide if you, well, redirect the traffic towards one application on the other application. And then once you distribute and replicate the entire application logic, then you need to synchronize how these replicas will interact and access the information tier. But on the other way around, in this case, since everything is self-contained and it's completely isolated, I mean, whenever we need to scale the system, we can scale the single microservices. Then we can, bootstrap and start up another shopping cart service, for example, in a fraction of seconds, because these are microservices, and then so bootstrapping a microservice is very fast, and then we can create many different replicas of the same microservice. Only the microservice that we need. We don't need to replicate the entire application, but only the specific functionality that is, that we need to scale at a given moment in the time. Okay, guys, that's all for today. I really hope that you enjoy. I mean, I don't know if you have any question. You can write on the chat right now, or sending me an email, or I don't know, have make an appointment, or whatever, or just ask Jesper, and then Jesper will forward me all your questions. So thank you very much, and see you around.